Okay, so we're going to go over logarithms. They are, so you have things like squaring. Squaring means repeated multiplication, or twice, something times itself. You could cube, which is something times itself times itself. To undo cubing, you would use the cubed root. That's the inverse of that. To undo squaring, you would use the square root. If you don't write anything up here, it's assumed to be a 2. With squaring, though, because negative x times negative x would make x squared, x times x would make x squared, you don't know if you're going to get a positive or negative because of that. Same with fourth powers and even powers. But just like how, squaring and square rooting are inverse operations. If I did, square root of x squared or square of square root, you're going to get basically x. Maybe it's positive or negative, but you undo the operations when you apply the inverse operation. Hello? No. Carly and Shay? Okay. Yep. I did attendance. I don't know why they're asking me. Okay, so we have inverse operations. On the left here, I have different versions of exponentiation. So whereas before, when you take something to when you have a variable raised to a numerical power, like 2 or 3, you multiply whatever that x is by itself that many times. The exponentials are a little different because they are a number raised to a variable. So you're going to multiply that number by itself a variable number of times. So the variable tells you how many times you're going to multiply it by itself. So if you don't multiply it by itself at all, it's just 1. If you multiply it by itself once, you get that number. Twice, you get the number squared. 3 times, you get the number cubed, like that. Now, if you plotted this, so like 0, 1, 2, 3, and let's say we're talking about 2 to the x. Well, at 0, you have 1. At 1 power, 2 to the 1, you have 2. So we have a number here, a number here. At 2 squared, you have 4. And we can fill in the gaps on those little points. And so the square root can handle decimal values like 2 to the 1.1. And that's just here. So you can fill in the gaps. So it's a little weird. What's 2 times itself 1.1 many times? That's kind of weird to think about. But it works. You're kind of just filling in the gaps on this graph with the dots. And you can do decimal values which go in between. But it's really on this curve, this exponential growth curve. So that's exponentiation. So 2 to the 5 equals 32. 2 to the 10 equals 1024. Things like that. So if you multiply 2 by itself 5 times, you get 32. You multiply 2 by itself 10 times, you get 1024. Log base 2 of a number will tell you what power of 2. How many times do I have to multiply by 2 to get to 1024? So sometimes we explain it like you have this little growth ray. I don't know, whatever you want to think of. And you can make an object expand, right? So if you have the dial set to 2, you're going to double every, let's say, minute. So if I hit it for a minute, it'll double in size. If I hit it for 2 minutes, it'll quadruple in size. It'll double again. If I hit it for 3 minutes, it will times 2 times 2 times 2. So it'll be 8 times bigger. That's so like if you hold the growth ray on it for so many units of time, you can multiply it by that many times 2. So if I hit it for 5 minutes, I would do 2 times 2 times 2 times 2 times 2. So I'd make it 32 times bigger. Log basically says if I do log base 2 of that big thing, it'll tell me how many doublings it took for me to get to that big number. So how many times do I have to multiply by 2 to get to 1024? So we'll do a couple of those. How about if I do log base 3 of 9? What would that be?
3.
Not 3.
9.
No. How many times do I have to multiply 3 by itself to get to 9?
Twice.
Twice, right? How about if I did log base 4 of 64?
Good question.
How many times do I have to multiply 4 by itself to get to 64?
I'm going to say 7.
Try it on your calculator. 4 times 4 times 4. How many times?
64?
Yeah.
60.
No. No. 4 times 4.
I got it.
Oh!
How many times do I have to do 4? Not no.
Yeah.
4 times 4 is 4.
So 3 4s, right?
Yeah.
Yeah. 4 to the third. So if I converted this to exponential form, this would say 3. Keep the base. The base stays the same. So base 3 to the second power makes 9. Base 4 to the third power makes 64. Does that make any sense? How about log base 5 of 125?
3.
It's 3, right? So 5 to the third makes 125. Is that all right?
Indeed.
All right, so here's a way that you can estimate logs. So like, let's say I say, what's log base 5 of 100? Well, 5 to the 0 is 1. 5 to the 1 is 5. 5 to the 2 is 25. And 5 to the 3 is 125. So I can tell that it's got 100 is between 25 and 125. So the power of 5 that I need here, 5 to the what makes 100. It's going to be a number, a decimal between 2 and 3. It's probably going to be closer to 3. So I'm going to guess something like 2.8. I don't know. But go ahead and try to raise 5 to the 2.8, and let's see what we get. You still have my calculator, John? You still have my calculator?
I'll put it over there
Where?
by the hand sanitizer.
Okay. So I'm going to raise 2 to the 2.8. That didn't work. Oh, 5 to the 2.8. Whoops, 5 to the 2.8. And I get 90.5, about 90.6. So not quite 2.8, maybe 2.9. That's 106. So you can kind of estimate, so maybe 2.85, maybe 2.85. Raise that to that power. So I'm sorry, there should be a 5 down here. 5 to the 2.85. I get 98.2 about. So you can kind of approximate that way. So how would we do it exactly? So I'm going to say, thank you. Log base 5 of 100. Well, you don't have a log base 5 on your calculator, but there is a change of base formula. So this is the same as any log you want. It could be log base 2, log base 10. Natural log is log base e, but you can do natural log of 100 divided by natural log of 5. That's called the change of base. Formula. So if I don't know what log base 5 of 100 is, I can take any log that I want of 100 of the argument divided by that same log of the base. So notice on your calculator you have a log button on the left probably and a natural log, ln. So if you need to know log base 5 of 100, how many times do I have to multiply 5 to make 100? Just do the logs that you have. So I have natural log, ln. I'm going to do ln of 100 divided by ln of 5. Yeah. So the correct answer was 2.861353116. Oops. There we go. So you can get it exactly with logs. So logs help you solve exponential equations. So now there's a nice trick. So let's say I say 5 to the, here's two ways of doing it. 5 to the x is equal to 80. Okay, so what should x be to make that equal to 80? We're going to do it twice here, just to show you how it works. Okay, on the left, I'm going to choose a particular log that's nice. So I'm going to do log base 5 of 5 to the x, log base 5 of 80. The reason why I chose log base 5 was because the base of my exponent, of my exponential on the left, was 5. So if I do log base 5, the properties of logs give you a couple of tricks. One, if you have an exponent, you can bring it down to multiply in front. So I'm going to turn this into x of log base 5 of 5. The exponent came down, equals log base 5 of 80. Now, how many times do I have to multiply 5 by itself to get to 5? Yeah, just once, right? So this is just 1. Anytime you have a log with this, of a number that's the same base as that number, that's just 1. So x times 1 is just x, so it kind of goes away. And then, so the x has to be log base 5 of 80. That would be the answer. But normally your calculator can't do log base 5 of 80. So I've got to do the change of base formula. So I'm going to choose the logs that I have on my calculator, like natural log of 80 over natural log of 5. That's how you compute log base 5 of 80. So I'm going to do natural log of 80 divided by natural log of 5. And I get, you guys have it? This natural log of 80 divided by natural log of 5. Yeah?
May I go develop my calculator in Mr. Carty's room?
Yeah. You guys have an answer?
Yeah, yeah. I don't have it. Oh, you don't have it? What's it?
Log base 80 over log base 5.
Is it just 5
Oh, like-
80?
Over?
Yeah. Divide by.
0.0625?
No.
Darn. I tried.
Log base 80 over what?
Log 80 over log 5.
Trying to guess. I used a calculator.
Is that some formula?
Yeah.
2.7227063.
Sounds good. So approximately 2.723.
But how'd you get that?
Have the best calculator.
Oh,
Okay. Now,
started.
choosing a log like that, like log base 5, is nice because it gets rid of the log on the left. But you're going to get log base 5 on the right, so you're probably going to have to use the change of base formula anyway. So honestly, it doesn't really matter if you choose the right log or not. Any logs will work. So I'm going to do on the right the same thing, only this time I'm going to use natural log right away. So I'm going to use natural log of 5x equals natural log of 80. The x comes down in front. X natural log of 5 equals natural log of 80. And then I just have to divide by natural log of 5 on both sides. And I get x is equal to natural log of 80 over natural log of 5, which is what we had before. And I know that that's approximately 2.723. So I would just use natural log all the time because it's always going to work. Your calculator has natural log. And even if you tried to use a clever log, at the end, you're probably going to have to use the change of base formula anyway. So you're probably just going to come to here anyway. So I would just pretty much always use ln. And so that should work. All right, so here's a couple types of questions that you'll have. And this is how you're going to use logs to solve them. You might get something like 2 to the x plus 1 is equal to 2 to the 3x minus 5. I don't know. Something like that. Or let me say 3. So they have different bases. Okay. So what number for x makes 2 give me, actually, I'm going to do that the other way, actually. I'm going to flip those. I think it'll just work out easier. So 3 to the something equals 2 to the something. What value of x makes that true? Are there any values of x? Hopefully I came up with one that's solvable. So I'm going to take natural log of both sides. That's how I'm going to get the exponents down. Okay, so I take the natural log of both sides. So just like always in algebra, if you do something to the left side, you got to do the same thing to the right side to keep it equal. It's like a scale. You got to balance the scale in order to maintain equality between the two sides. So you have to do the same to both sides. Okay, why did I choose to do the log? Well, because I want the variables to come down so that I can solve for them. So this is going to bring the variables down. So I can say x plus 1 comes down, natural log of 3. Now, this is not natural log times 3, it's natural log of 3. It's a function, and I'm inputting 3 into that function. So this is a number, and this is x plus 1 over here. Equals, then I get 3x minus 5. And that both of those terms are multiplied by natural log of 2, which is a number. It's some decimal number. So I'm going to move, I'm going to divide both sides by natural log of 2. So I can get them together. Natural log of 3 over natural log of 2. That's going to equal 3x minus 5. And this is going to multiply x plus 1. Now, again, this is just a number. So it's just like if it were a 2 or a 3 or a negative 1. I can distribute it in like that. This one's kind of a harder one than I anticipated, but we'll do it anyway. This is not the easiest one I could have started with. I'm going to call this number here, this natural log of 3 divided by natural log of 2. I mean, you can compute it right now. So like natural log of 3 divided by natural log of 2, that's about 1.585. So it's a number. It just looks a little nasty. So I'm going to rewrite it. I'm going to rewrite this whole expression. And I'm going to plug this in later, what natural log of 3 is over natural log of 2. Right now, I'm going to call it the number n. Okay? So I'm going to write x plus 1 n equals 3x minus 5, where n is equal to natural log of 3 over natural log of 2, which is approximately 1.585. All right, so then I just got to solve for x. So I'm going to distribute the n. So I get n times x plus n equals 3x minus 5. Oh, actually, no, I want to solve for x, right? So I'm going to subtract n from both sides. So I get nx is equal to 3x minus 5 minus n. N is just a number. And then I'm going to subtract 3x from both sides. And I get n minus 3 times x equals minus 5 minus n. Now I just have to divide by n minus 3. And so x will be equal to minus 5 minus n all over n minus 3. So n was about 1.585. So I just got to plug that in. I'll just sort of highlight that. So use 1.585 wherever n is. And so you should get minus 5 minus 1.585 divided by 1.585 minus 3. And so x is about 4.654. So that's how you use it, basically. You apply log to both sides, you bring down the exponent, and then solve for the exponent. So that one was a little bit more complicated because I chose the two bases that are different. We'll do a few more examples. I'll try to start with an easier one this time. Let's try 5 to the 3x plus 1 is equal to 72. All right. So I'm going to just take log of both sides. Can you guys see that okay? Let me switch colors there. So the natural log of 5 to the 3x plus 1 is natural log of 72. So take the same of both sides. You can bring the exponent down now. 3x plus 1 times natural log of 5 equals natural log of 72. I'll divide by natural log of 5 on both sides because it's just a number. And I get 3x plus 1 is equal to natural log of 72 over natural log of 5. Subtract 1 from both sides. And then I have 3x is equal to this. And then I'll divide by 3. And that's how you solve that. So x is 1/3 of whatever this is. So I'll take natural log of 72 divided by natural log of 5. That gives me about 2.66. Subtract 1 and then divide that by 3. And so this comes out to be approximately 0.552. So that's the trick. Just use log to bring down the exponents. You're going to get a nasty number, a decimal number. I'm not plugging them in. I'm just leaving them as logs. That's the exact way to solve for it. But I'll do one in just a second where we will switch it out for the decimals.
Today? She said she'd play or tomorrow.
I'm going to do,
I was thinking, I was like, I work yesterday.
I'm going to do another one here. Let's say we have, let's say we have 6 to the 2x plus 1. Let's say minus 5. Yeah. Equals minus 5. I'm sorry, minus 5 equals 200. Say regular time.
Mass day, wasn't it?
Is mass day different?
I thought it was 55 on mass day.
Is it?
Yeah, it's mass.
Oh, okay. You're probably right. I don't know. I thought we were regular time. That makes sense though. Yeah, I think you're probably right. So let me wrap this up just for the video real quick. We got 3 minutes. All right, you want to get the power by itself. So I'm going to add 5 to both sides. So this is going to become 205 on the right, 6 to the 2x plus 1 on the left. Use natural logs now. So 2x plus 1 comes down. Natural log of 6, natural log of 205. And then divide by natural log of 6 on both sides. And so the right becomes natural log of 205 over natural log of 6, which is about 9.5376. And then just solve for x. Crap. That's about 4.2688. I'll probably just push this back and we'll go over, because I still want to explain more with the exponentials and logs next time. So you guys don't have to worry about it for today, I guess. So you get a free day. Thanks to mass. All right, you guys have a good next period, and then have a great rest of the day. Juniors go to the basement, seniors go to the
I hate going to basement.